At the end of this video, you should be able to describe an object's acceleration in terms of its mass and the net force acting on it, predict the direction and magnitude of the acceleration caused by a known net force, and identify action-reaction pairs. Chapter 4, Section 3, Newton's second and third laws. Newton's second laws. From Newton's first law, we know that an object with no net force acting on it is in a state of equilibrium. We also know that an object experiencing a net force undergoes a change in its velocity. But exactly how does a known force affect the motion of an object? Force is proportional to mass and acceleration. Imagine pushing a stalled car through a level intersection, as is shown on the screen here. Because a net force causes an object to accelerate, the speed of the car will increase. When you push the car by yourself, however, the acceleration will be so small that it will take a long time for you to notice any increase in the car's speed. If you get several friends to help you, the net force on the car is much greater, and the car will soon be moving so fast that you will have to run to keep up with it. This change happens because the acceleration of an object is directly proportional to the net force acting on the object. Note that this is an idealized example that disregards any friction force that would hinder the motion. In reality, the car accelerates when the push is greater than the frictional force. However, when the force exerted by the pushers equals the frictional force, the net force becomes zero, and the car moves at a constant velocity. Experience reveals that the mass of an object also affects the object's acceleration. A lightweight car accelerates more than a heavy truck if the same force is applied to both. Thus, it requires less force to accelerate a low-mass object than it does to accelerate a high-mass object at the same rate. Newton's second law relates force, mass, and acceleration. The relationships between mass, force, and acceleration are quantified in Newton's second law. According to Newton's second law, if equal forces are applied to two objects of different masses, then the object with greater mass will experience a smaller acceleration, and the object with less mass will experience a greater acceleration. In equation form, we can state Newton's law as follows. The sum of F is equal to ma. In this equation, a is the acceleration of the object, and m is the object's mass. Note that sigma, or that weird-looking E, is the Greek capital letter, again sigma, which represents the sum of the quantities that come after it. In this case, F represents the vector sum of all external forces acting on the object, or the net force.
Imagine a hockey puck sitting on an air hockey table. The downward force of the puck's weight is exactly canceled by the force of the air jets pushing up. If there is no net force on the puck, Newton's first law is enough to understand the motion. But what if there is an unbalanced force? Imagine a hockey puck with a sail. The force of the wind from the fan can slow down the puck, stop it, and make it accelerate in the other direction. We can learn about the amount of force that was used if we measure the mass of the puck and its acceleration. Newton's second law shows the exact relationship between the net force on an object measured in newtons, its mass measured in kilograms, and its acceleration measured in meters per second squared.
Newton's third law. A force is exerted on an object when the object interacts with another object in its environment. Consider a moving car colliding with a concrete barrier. The car exerts a force on the barrier at the moment of collision. Furthermore, the barrier exerts a force on the car so that the car rapidly slows down after coming into contact with the barrier. Similarly, when your hand applies a force to a door to push it open, the door simultaneously exerts a force back on your hand. Forces always exist in pairs. From examples like those discussed in the previous segment, Newton recognized that a single isolated force cannot exist. Instead, forces always exist in pairs. The car exerts a force on the barrier, and at the same time, the barrier exerts a force on the car. Newton described this type of situation with his third law of motion. An alternative statement of this law is that for every action, there is an equal and opposite reaction. When two objects interact with each other, the forces that the objects exert on each other are called an action-reaction pair. The force that object 1 exerts on object 2 is sometimes called the action force, while the force that object 2 exerts on object 1 is called the reaction force. The action force is equal in magnitude and opposite in direction to the reaction force. The terms action and reaction sometimes cause confusion because they are used in a little differently in physics than they are in everyday speech. In everyday speech, the word reaction is used to refer to something that happens after and in response to an event. In physics, however, the reaction force occurs at exactly the same time as the action force. Because the action and reaction forces coexist, either force can be called the action or reaction. For example, you could call the force that the car exerts on the barrier the action and the force that the barrier exerts on the car the reaction. Likewise, you could choose to call the force that the barrier exerts on the car the action and the force that the car exerts on the barrier the reaction. Action and reaction forces each act on different objects. One important thing to remember about action-reaction pairs is that each force acts on a different object. Consider the task of driving a nail into wood, as is illustrated on the screen here. To accelerate the nail and drive it into the wood, the hammer exerts a force on the nail. According to Newton's third law, the nail exerts a force on the hammer that is equal to the magnitude of the force that the hammer exerts on the nail. The concept of action-reaction pairs is a common source of confusion because some people assume incorrectly that the equal and opposite forces balance one another and make any change in the state of motion impossible. If the force that the nail exerts on the hammer is equal to the force that the hammer exerts on the nail, why doesn't the nail remain at rest? The motion of a nail is affected only by the forces acting on the nail. To determine whether the nail will accelerate, draw a free body diagram to isolate the forces acting on the nail, as is shown in figure 3-3 or on the screen now. The force of the nail on the hammer is not included in the diagram because it does not act on the nail. According to the diagram, the nail will be driven into the wood because there is a net force acting on the nail. Thus, the action-reaction pairs do not imply that the net force is on either object is zero. The action-reaction forces are equal and opposite, but either object may still have a net force acting on it. Field forces also exist in pairs. Newton's third law also applies to field forces. For example, consider the gravitational force exerted by Earth on an object. During calibration at a crash test site, engineers calibrate the sensors in the heads of crash test dummies by removing the heads and dropping them from a known height. The force that Earth exerts on the dummy's head is Fa. Let's call this the force of action. What's the reaction? Because Fa is the force exerted on the falling head by Earth, the reaction to Fa is the force exerted on Earth by the falling head. According to Newton's third law, the force of the dummy on Earth is equal to the force of Earth on the dummy. Thus, the falling object accelerates toward Earth. Earth also accelerates toward the object. The thought that Earth accelerates toward the dummy's head may seem to contradict our experience. One way to make sense of this idea is to refer to Newton's second law. The mass of Earth is much greater than that of the dummy's head. Therefore, while the dummy's head undergoes a large acceleration due to the force of Earth, the acceleration of Earth due to this reaction force is negligibly small because of Earth's enormous mass.
Newton's third law asserts that forces always act in pairs. For example, a car accelerates by causing its wheels to turn and push against the road. It is the force of the road pushing back against the car that makes the car go. Note that the forces are simultaneous. The car puts a force on the road at the same time that the road puts a force back on the car. The forces act in pairs and have the same magnitude, but it is a mistake to think that the forces together would cancel each other out. The force on the car makes the car accelerate. And the force on the road, which is firmly attached to the earth, makes the earth accelerate, although only by a very small amount. Adding the force on the road and the force on the car does not make sense because the forces are applied to different objects with different observed results. A force on the earth doesn't affect the car, and a force on the car doesn't affect the earth. Newton's third law holds for non-contact forces as well. Consider the effect of the earth's gravity on a paper airplane. When the earth pulls downwards on the airplane with a force of 5 newtons, the airplane pulls upwards on the earth by the same amount.
At this point, you should be able to describe an object's acceleration in terms of its mass and net force acting on it, predict the direction and magnitude of the acceleration caused by a known net force, and identify action-reaction pairs.